In 1990, inside a basement laboratory at the National Institute of Standards and Technology in Boulder, Colorado, a team of 4 physicists did something that sounds like it belongs in a science fiction movie. They took about 5,000 atoms of beryllium, cooled them down to 1/4 of a degree above absolute zero, and then they watched them. That was the experiment. They watched atoms, and by watching those atoms, they prevented them from changing. Not metaphorically, not in the way that staring at a pot on the stove makes it feel like the water takes longer to boil. They literally, physically, measurably prevented atoms from transitioning from one quantum state to another. The more they watched, the more frozen the atoms became. With 64 measurements during a period where the atoms should have completely changed states, the transition probability dropped to less than 1%. The atoms could not move because someone was looking at them. The lead experimentalist was a guy named Wayne Itano. His boss was David Wineland, who would go on to win the Nobel Prize in 2012, partly for the techniques he developed during this work. And the theoretical prediction they were testing had been made 13 years earlier by 2 physicists at the University of Texas named Baidyanath Misra and George Sudarshan. Misra and Sudarshan had named their discovery after a Greek philosopher who lived 2,500 years ago, a man named Zeno, a man who argued, using nothing but logic, that motion itself is impossible. They called it the Quantum Zeno Effect, and it might be the strangest thing in all of physics. Here is the premise, stated as simply as I can state it. In the quantum world, if you observe a system frequently enough, you can prevent it from changing. You can freeze an unstable atom so it never decays. You can stop a particle from tunneling through a barrier it should easily pass through. You can hold a quantum state perfectly still while the laws of physics scream at it to evolve, all by looking at it. This is not a fringe theory. This is not speculative. This has been experimentally confirmed in laboratories around the world for over 30 years, using trapped ions, ultra-cold atoms, superconducting circuits, nitrogen vacancy centers in diamond, and quantum dots. It is real, it is repeatable, and it is, right now, being engineered into quantum computers, atomic magnetometers, and even our understanding of how birds navigate the planet. But to understand why observation freezes reality at the quantum scale, we need to start somewhere unexpected. We need to start with a philosopher in ancient Greece who bit off a tyrant's ear. And we need to talk about arrows, 2,500 years before anyone had ever heard of quantum mechanics, in a small Greek colony called Elea on the western coast of what is now southern Italy. A philosopher named Zeno was causing problems. Zeno of Elea was born around 490 BCE to an aristocratic family. His teacher was Parmenides, the founder of what historians call the Eleatic school of philosophy, and Parmenides had a radical idea. He believed that reality is one, not many. One, a single, eternal, unchanging, indivisible thing. Change is an illusion. Motion is an illusion. The diversity you see around you, the movement, the growth, the decay, all of it is a trick your senses play on you. True reality just is. It does not become. It does not move. It does not change. Now, you can probably imagine how this went over. People thought Parmenides was nuts, and this is where Zeno came in. Zeno's job was not to prove Parmenides was right. His job was to prove that everyone else was wrong. Aristotle called Zeno the inventor of dialectic, which is essentially the art of winning arguments by showing that your opponent's position leads to absurdity. Zeno was not trying to advance positive claims. He was trying to defend his teacher Parmenides by demonstrating that opposing views led to self-contradiction. "If you believe in motion and plurality," Zeno said, "I will show you that your beliefs produce conclusions so absurd that you will wish you had never believed them." He was, by all accounts, formidable. Plato's dialogue Parmenides records that Zeno and his teacher visited Athens together around 450 BCE, when Zeno was about 40 years old and a young Socrates was around 20. The visit suggests that the Eleatic school had enough intellectual prestige to command attention in Athens, the center of the Greek philosophical world. And there is one more thing about Zeno that has nothing to do with physics or mathematics, but tells you something about the kind of person he was. According to multiple ancient sources, Zeno was involved in a conspiracy to overthrow a tyrant who ruled Elea. The tyrant's name varies in different accounts, Nearchus or Demolus, depending on the source. When the conspiracy was discovered and Zeno was captured, he was tortured for the names of his co-conspirators. He refused to give them up. According to Diogenes Laertius, Zeno asked to whisper the names into the tyrant's ear, and when the tyrant leaned close, Zeno bit down on his ear and refused to let go until he was killed. Other versions say he bit off his own tongue and spat it at the tyrant rather than betray his friends. Valerius Maximus records that Zeno pounded the tyrant's face while biting him and was not released until he was stabbed to death. Whether the details are precisely accurate across 2.5 millennia of retelling, the core story is consistent across multiple independent sources. Zeno of Elea, the man who argued that motion is impossible, died in violent motion, resisting tyranny with his body after defending truth with his mind. He was, in the fullest sense, a man willing to die for what he believed. That his paradoxes would one day name a quantum effect in a laboratory in Colorado would have been entirely beyond his imagination. But the spirit of relentless inquiry, of refusing to accept easy answers, of demanding that the universe explain itself logically, that spirit connects Zeno's ancient arguments to modern quantum physics in a way that goes deeper than just a clever name. According to the 5th century commentator Proclus, Zeno wrote a book containing 40 of these paradoxes. Most of them are lost to history, but a handful survived through Aristotle's writings, and they are some of the most famous thought experiments in the history of human reasoning. You have probably heard of at least one, Achilles and the tortoise, the one where the fastest runner in Greek mythology can never overtake a turtle, because by the time Achilles reaches where the tortoise was, the tortoise has moved a little further, and by the time Achilles reaches that new spot, the tortoise has moved again, and this process repeats infinitely. An infinite number of tasks to complete, each taking some amount of time. How can you finish infinitely many things? There is another one called the dichotomy, which is equally maddening. To cross a room, you first have to cross half the room, but before you can cross half the room, you have to cross a quarter of it. Before a quarter, an eighth. Before an eighth, a 16th. There are infinitely many steps before you can even start moving. You need to complete an infinite sequence just to take a single step. These paradoxes feel like tricks, like clever wordplay that should be easy to dismiss. But they are not. They are probing something real about the relationship between the finite and the infinite, between the discrete and the continuous. Can a finite distance contain infinitely many points? Can a finite time interval contain infinitely many subintervals? If so, how do you traverse infinitely many of them in finite time? These questions sound simple, but they are not. And the answers required mathematical machinery, convergent infinite series, the theory of limits, the epsilon-delta definition of continuity that was not available until the 19th century, over 2,000 years after Zeno asked the questions. The specific resolution for Achilles and the tortoise is that an infinite sum of decreasing terms can converge to a finite value. If each catch-up step takes half as long as the previous one, the total time is finite, even though the number of steps is infinite. 1/2 plus 1, quarter plus 1/8 plus 1/16, and so on, forever equals exactly 1. Infinite steps. Finite total. Achilles overtakes the tortoise. The math works, but it took Augustin Louis Cauchy, Karl Weierstrass, Richard Dedekind, and Georg Cantor, working through the 1800s, to put this on a rigorous foundation. Zeno's paradoxes were not fully resolved until over 2,300 years after they were posed. Bertrand Russell wrote that after 2,000 years of continual refutation, Zeno's arguments were reinstated and made the foundation of a mathematical renaissance. But the paradox that matters for our story is a different one. The arrow. Imagine an arrow in flight. At any single instant, any frozen moment in time, the arrow occupies a space exactly equal to its own length. It is not in the process of moving to a new position, because within a single instant, no time passes. You cannot move through space if no time elapses. So at that instant, the arrow is at rest. Pick another instant. Same thing. At rest. Pick any instant you want. At every single one of them, the arrow is motionless. Here is Zeno's punchline. Time is made up of these instants. If the arrow is at rest at every instant, and time is just a sequence of instants, then the arrow is at rest for the entire duration of its flight. The flying arrow is motionless. Now your brain is probably already fighting this. Obviously, arrows move. You can see them move. You can get hit by one, and it moves right through you. Zeno knew this. He was not stupid. The point was not that arrows are secretly stationary. The point was that our concepts of time, motion, and infinity contain hidden contradictions that we usually ignore. And he was right about that. It took mathematicians over 2,000 years to develop the tools, limits, calculus, set theory to formally resolve Zeno's paradoxes. Bertrand Russell wrote that after 2,000 years of continual refutation, Zeno's arguments were reinstated and made the foundation of a mathematical renaissance. But here is where the story takes a turn that Zeno could never have anticipated. Because in 1977, two physicists at the University of Texas would discover that in the quantum world, Zeno's frozen arrow is not a paradox at all. It is a prediction. And it is correct. The watched arrow really does not fly. To understand why, we need to talk about what makes quantum mechanics different from everything that came before it. And the key difference, the thing that separates the quantum world from the everyday world you experience, is what happens when you look at something. In classical physics, the physics of Newton and billiard balls and planets, observation is passive. You can look at a baseball as much as you want, and it will not change its trajectory. You can measure the speed of a car without affecting the car. The act of gathering information about a system does not change the system. This is so obvious in everyday life that it barely seems worth stating. In quantum mechanics, this is spectacularly wrong. A quantum system, say an electron or an atom, does not exist in a single definite state the way a baseball does. Before you measure it, it exists in what physicists call a superposition, a blend of multiple possible states simultaneously. An atom that can be in energy level 1 or energy level 2 is, before measurement, in a combination of both. Not one or the other, both. The math describes this with a wave function, a mathematical object that encodes the probabilities of every possible outcome. When you measure the system, something dramatic happens. The wave function collapses, the superposition disappears, the atom snaps into one definite state, level 1 or level 2. Not both anymore, just one. And this is not a failure of your instruments. This is not a limitation of your knowledge. This is, as far as anyone can tell, a fundamental feature of how reality works at the quantum scale. This is called the measurement problem, and it has been the central mystery of quantum mechanics for 100 years. What counts as a measurement? Why does looking at the system change it? Does the wave function actually collapse, or does something else happen? Different interpretations of quantum mechanics give radically different answers, and none of them are fully satisfying. But whatever the interpretation, the mathematical prediction is clear and experimentally confirmed. Measurement changes quantum systems. Now here is the part that leads to the Zeno effect. When a quantum system evolves over time, it does so through superposition. An atom in energy level 1 that is transitioning to energy level 2 does not jump instantaneously. It gradually evolves through a superposition of both states. At the start, it is all level 1. Then it is mostly level 1, with a little level 2 mixed in. Then half and half. Then mostly level 2. Then all level 2. The transition happens smoothly through a superposition that shifts over time. But if you measure the atom before the transition is complete, you collapse that superposition. You force it to pick. And here is the critical insight. If you measure very early in the transition, when the atom is still mostly in level 1, the probability of finding it in level 1 is very high. The math says the transition probability at short times is quadratic, meaning it starts incredibly slowly and then accelerates. If you measure during that initial slow period, you almost certainly find the atom still in level 1. And when you do, the wave function collapses back to level 1 completely. The clock resets. The transition starts over from 0. Measure again quickly. Same thing. The atom has barely had time to start transitioning. You find it in level 1 again. Collapse. Reset. Measure again. Level 1. Reset. Measure again. Level 1. Reset. If you keep measuring fast enough, the atom never has a chance to accumulate enough transition probability to actually change state. You keep catching it before it has gotten anywhere. You keep resetting the clock. The atom is frozen, not because you are doing anything to it in the classical sense, not because you are pushing it or holding it or applying a force. You are freezing it purely by looking at it, by collapsing its wave function back to the starting state over and over and over again. That is the Quantum Zeno Effect. And the math is airtight. In the limit of truly continuous observation, the survival probability, the chance the system remains in its initial state, approaches 100%. The system never changes, ever. The watched quantum pot never boils. Let me give you an analogy that captures the essential idea. Imagine a ball sitting at the very top of a gentle hill. If you leave it alone, it will start rolling, slowly at first, barely perceptible, then faster and faster as gravity accelerates it. After enough time, it is barreling downhill, and nothing short of a wall will stop it. That slow start, followed by rapid acceleration, is the quantum transition. The quadratic phase is the ball barely starting to creep. The exponential phase is the ball picking up serious speed. Now imagine, you can pick the ball up and place it back at the exact top of the hill. If you do this while the ball has barely started moving, you have lost almost nothing. It starts the slow creep again from zero. Pick it up again, back to the top, creep, pick up, back to the top, creep. If you do this fast enough, the ball never gets out of first gear. It never reaches the phase where it accelerates rapidly downhill. You keep resetting it during the slow part, over and over and over. That is what quantum measurement does. It catches the system during that initial slow period and resets it to the starting state. Do it fast enough, and the system never reaches the exponential regime where the transition probability grows quickly. The reason this works mathematically is subtle and important. If the transition probability grew linearly from the start, frequent measurements would not help. Measure 10 times during the same total period, and each measurement would catch the system having made roughly 1/10 of its transition. 10/10 still add up to 1, a full transition. But because the growth is quadratic, the math works differently. The probability in a short interval goes as the square of the time. Cut the interval in half, and the probability drops to 1/4, not 1/2. Cut it to 1/10, and the probability drops to 1/100th. 10 measurements of 1/100th each give a total of 10 1/100ths, which is 1/10th. Far less than the full transition you would get with no measurements. This is why the Zeno effect gets stronger the more you measure. With 100 measurements, each interval has a transition probability of 1/10,000th, and 100 of those add up to 1/100th. With 1,000 measurements, it drops to 1/1,000,000th total. The more frequently you measure, the more dramatic the freezing. In the limit of continuous measurement, the total transition probability goes to 0, perfect freezing. And all because quantum transition probabilities are quadratic at short times rather than linear. This is the mathematical heart of the Quantum Zeno Effect. It is not magic. It is not mysterious. It is a straightforward consequence of how quantum systems begin their transitions. But the implications are unlike anything in classical physics. Think about how strange this is. In the classical world, looking at something does nothing. In the quantum world, looking at something is the most powerful thing you can do to it. You can freeze reality itself just by paying attention to it. And the strangest part might be this. Nobody believed it would actually work when it was first proposed. The first person to notice this peculiarity was, of all people, Alan Turing. Yes, that Alan Turing, the father of computer science, the man who cracked the Enigma code, the man whose theoretical work on computation created the foundation for every computer you have ever used. In the last years of his life, Turing was working on fundamental physics, and in 1953, during conversations with mathematician Robin Gandy, he stumbled onto something odd in the standard equations of quantum mechanics. After Turing's death in June 1954, Gandy described the discovery in a letter to M.H.A. Newman. He called it the Turing paradox. It is easy to show, Gandy wrote, using standard theory, that if a system starts in an eigenstate of some observable and measurements are made of that observable n times a second, then even if the state is not a stationary one, the probability that the system will be in the same state after, say, 1 second tends to 1 as n tends to infinity. In other words, continual observation will prevent motion. Turing and Gandy brought this to several theoretical physicists and were essentially brushed off. The physicists said that continual observation is not possible in practice, so the paradox was irrelevant. But as Gandy noted, there was nothing in the standard textbooks, not in Dirac's canonical text, not anywhere, that explained why continuous observation was impossible. The paradox exposed an inadequacy in quantum theory as usually presented, and the physics community shrugged. Turing never published this insight. He died at 41 in June 1954 from cyanide poisoning, ruled a suicide but debated by historians ever since. And his observation about quantum measurement sat in a private letter for decades. 13 years later, in 1967, two Swedish physicists at the Institute of Theoretical Physics in Gothenburg did publish something related. Eike Beskow and Josef Nilsson wrote a paper in Archiv for Physik, pointing out that the mathematics of quantum mechanics predicted an unstable particle being tracked in a bubble chamber would not decay. The continuous observation provided by the bubble chamber should freeze the particle. It was a brief suggestion buried in a longer paper about unstable systems and decay laws, and it did not cause a stir. Around the same time, Soviet physicist Leonid Kalfin had been doing important foundational work on the mathematical behavior of quantum decay. His 1958 paper in Soviet Physics, GTT, established that quantum decay cannot be purely exponential at very short times. There must be an initial period where the decay probability grows quadratically, not exponentially. This was the mathematical key that would eventually make the Zeno effect possible, because it is that short-time quadratic behavior that allows frequent measurements to keep resetting the clock. But Kalfin's work was technical and mathematical, and the connection to observation freezing systems was not made explicit. The breakthrough came in 1977 from two physicists working at the University of Texas at Austin, and one of them has a story that might be the most tragically underappreciated in all of modern physics. Enakal Chandi. George Sudarshan was born on September 16, 1931, in Palam, a small town near Kottayam, in the Indian state of Kerala. His family was Syrian Orthodox Christian, part of a community that traces its roots to the Apostle Thomas. Young George discovered physics almost by accident. Through his older brother's high school textbook, there was a passage about the simple pendulum, the kind of thing you see in a grandfather clock, a weight swinging back and forth on a string. The textbook explained the pendulum's behavior, but then noted that the derivation of the formula for its period was beyond the scope of the book. That sentence changed George Sudarshan's life. He became obsessed with finding that derivation, not because anyone told him to, not because it was assigned, because the book told him he could not do it, and he needed to prove the book wrong. It was a quality that would define his entire career, this compulsion to push past whatever boundaries someone placed in front of him. It was also a quality that would bring him extraordinary brilliance and extraordinary pain, because the boundaries he pushed against would eventually include the Nobel Prize Committee itself. Sudarshan studied at Madras Christian College in Chennai, earned his bachelor's degree, and moved to the Tata Institute of Fundamental Research in Bombay. In 1954, something transformative happened. Paul Dirac visited TIFR. This was Paul Dirac, one of the founders of quantum mechanics, the man who predicted the existence of antimatter, whose equation is etched into the floor of Westminster Abbey. Sudarshan was assigned to prepare Dirac's lecture notes, which meant spending extended time with one of the greatest physicists who ever lived. The experience gave young Sudarshan extraordinary confidence. He later described Dirac as the master himself, and the two became lifelong friends. From India, Sudarshan went to the University of Rochester in New York to work on his doctorate under Robert Marshak. And it was there, at the age of 26, that he made a discovery that should have won him the Nobel Prize. It did not. The story of Sudarshan and the weak interaction is one of the great injustices in the history of science, and I am going to tell it in some detail because it matters for understanding who this man was when he later turned his attention to the Quantum Zeno Effect. In the 1950s, physicists were struggling to understand the weak nuclear force, the force responsible for radioactive beta decay. The weak force was weird. It violated symmetries that the other forces respected, and nobody could figure out the correct mathematical form for how it worked. There were several possibilities, different combinations of vector, axial vector, scalar, tensor, and pseudoscalar interactions. Experimental data seemed to point in contradictory directions. Sudarshan, working with Marshak, did something bold. They systematically analyzed every single piece of experimental evidence and concluded that the correct form was V minus A, vector minus axial vector. This was radical because it required throwing out 4 separate experimental results that seemed to contradict it. Sudarshan and Marshak predicted that all 4 of those experiments were wrong. And here is the thing. They were right. Every single one of those experiments was later repeated with better techniques, and every single one confirmed the V minus A structure. But the credit went elsewhere, and the way it happened reads like a comedy of errors, except it was not funny for Sudarshan at all. Marshak did not let Sudarshan present their findings at the 1957 Rochester conference because Sudarshan was just a graduate student. Marshak himself gave a vague talk that did not clearly state their conclusion. Then Marshak had lunch with Murray Gell-Mann in Santa Monica and shared their V-A idea with him. Marshak submitted their paper to the conference proceedings, which had limited circulation, rather than to a major journal. Meanwhile, Richard Feynman and Gell-Mann wrote their own paper presenting the V-A theory and submitted it to physical review. The submission date was September 16th, 1957, George Sudarshan's 26th birthday. The Feynman and Gell-Mann paper appeared in January 1958 and was widely read. The Sudarshan and Marshak preprint circulated but was buried in conference proceedings that far fewer people saw. The physics community largely credited Feynman and Gell-Mann. And to his credit, Feynman knew this was wrong. He later said publicly that the V-A theory was discovered by Sudarshan and Marshak, publicized by Feynman and Gell-Mann. In a 1985 letter to Marshak, Feynman wrote that he hoped someday they could get this straightened out and give Sudarshan the credit for priority that he justly deserved, and that he wished he had not caused them such discomfort. But scientific credit, once established, is nearly impossible to redistribute. The V-A theory became a cornerstone of the standard model of particle physics. It was the foundation upon which Sheldon Glashow, Abdus Salam, and Steven Weinberg built the electroweak unification, which won them the Nobel Prize in 1979. Sudarshan's work was the first floor of that building, as he put it himself. If you give a prize for a building, shouldn't the fellow who built the first floor be given the prize before those who built the second floor? This was not the last time the Nobel Committee would overlook him. In 1963, Sudarshan developed what is called the diagonal representation in quantum optics, a mathematical tool showing that any quantum optical state can be expressed using coherent states. It became the fundamental language of modern quantum optics. The story goes that his colleague Emil Wolf came back from a conference in Paris discouraged that quantum coherence theory was going to be impossibly difficult. Sudarshan told him not to worry, worked furiously, and developed his complete theory. Wolf insisted that Sudarshan draft the paper immediately and send it by priority mail before going to lunch. In 2005, Roy Glauber received half the Physics Nobel Prize for his contribution to the quantum theory of optical coherence. Several prominent physicists wrote letters of protest to the Swedish Academy. Sudarshan himself wrote a letter that included a biblical allusion. Given to Glauber, he said, only what is his. Sudarshan was reportedly nominated for the Nobel Prize 9 times. 9 times. He never won. He developed a philosophical acceptance about it, writing in 1985 that it had been a sad but wise experience to recognize that the universality of science does not imply unbiased acclaim for scientific truth, and that if you have neither powerful alliances nor influential sponsors, you should learn to do science for its own sake and not be depressed by lack of appreciation. This was the man who, in 1977, together with his collaborator Baidyanath Misra, would give the world the Quantum Zeno Effect, a man who had already been robbed of credit for at least 2 Nobel-caliber discoveries, a man who understood, perhaps better than anyone alive, what it felt like to have the scientific establishment refuse to look at what you had done. The irony is almost too perfect. George Sudarshan, a physicist the world refused to watch, discovered that watching is the most fundamental act in quantum mechanics. Misra and Sudarshan's 1977 paper was titled simply The Zeno's Paradox in Quantum Theory. It appeared in the Journal of Mathematical Physics, Volume 18, and it was a rigorous mathematical proof of something that sounded impossible. An unstable particle, they wrote, will never be found to decay when it is continuously observed. The paper laid out the mathematics precisely. Take a quantum system in some initial state. Let it evolve for a short time. Then measure whether it is still in the initial state, if the time interval is short enough, the probability of finding it unchanged is very high, because quantum transition probabilities grow quadratically at short times, not linearly. Each measurement that finds the system unchanged collapses it back to the starting state. The evolution clock resets. Now divide the total time into n measurement intervals. As n gets larger, each interval gets shorter. The probability of surviving each individual measurement gets closer to 1, and the total probability of surviving all n measurements approaches 1 as n approaches infinity. In the limit of continuous observation, the system is frozen. Misra and Sudarshan chose the name Quantum Zeno Effect with deliberate care. They saw the parallel to Zeno's arrow paradox and recognized that what was a philosophical puzzle in the classical world became a physical prediction in the quantum world. At each measurement, the quantum system is found in its initial state, just as Zeno's arrow is found to be motionless at each instant. If every instant shows no change, and time is a sequence of such instants, the system never changes. But there is a crucial difference that makes the quantum version more than just a clever analogy. Zeno's classical paradox is resolved by calculus. The mathematics of limits and continuity shows that an infinite number of infinitesimal displacements can sum to a finite distance. The arrow does move. The math just needed to be more sophisticated than what was available in ancient Greece. The quantum Zeno effect is not resolved by better math. The math is what predicts it. The wave function formalism of quantum mechanics, the projection postulate, the Born rule for measurement probabilities, all of the standard mathematical machinery produces this result. It is not a paradox to be resolved. It is a prediction to be tested, and the prediction has a critical requirement. The measurements must happen faster than a characteristic timescale called the Zeno time. This is the timescale over which the transition probability is quadratic before it transitions to exponential behavior. For atomic transitions, the Zeno time can be incredibly short. For the hydrogen atom's 2p-1s transition, it is on the order of 10 to the minus 13 seconds. That is a tenth of a picosecond, 1/10 trillionth of a second. Think about what that means. To freeze a hydrogen atom's emission of a photon by watching it, you would need to measure the atom 10 trillion times per second. That is not just technically difficult. For many systems, it is physically impossible without destroying the system entirely. This is part of why the physicists who brushed off Turing's paradox in the 1950s were not entirely wrong. For many quantum systems, the measurement rate required for the Zeno effect is absurdly fast, but not for all systems, and that is what made the 1990 experiment at NIST so important. Baidyanath Misra deserves his own moment in this story before we move on. Born August the 25th, 1937, in Pithapatal in the Indian state of Orissa, now called Odisha, Misra followed a winding academic path from Utkal University to the University of Delhi to Yale to the University of Geneva, where he earned his doctoral degree in 1965. He bounced between continents, holding positions at Rochester, at Sambalpur University back in India, at the University of Colorado in Boulder. The critical year was 1975, when Misra visited the University of Texas at Austin and began collaborating with Sudarshan. Their combined expertise in mathematical physics, Misra's rigorous formal training, and Sudarshan's extraordinary physical intuition produced a paper that would generate over 500 citations and launch an entire subfield of quantum mechanics. After the Zeno paper, Misra went on to become a research professor at the International Solvay Institute in Brussels and eventually Dean of the School of Physical Sciences at Jawaharlal Nehru University in New Delhi. He received the Leonardo da Vinci Award from the Royal Belgian Academy of Sciences in 1986, but in the public consciousness, to the extent that the Quantum Zeno Effect's theorists are remembered at all, it is Sudarshan's name that comes up more often, partly because of the dramatic Nobel controversies, and partly because Sudarshan spent 47 years at the University of Texas building a legacy that extended far beyond this single paper. Sudarshan joined UT Austin in 1969 and stayed until his death in 2018. He became co-director of the Center for Particle Theory and trained generations of physicists. He contributed to an astonishing range of fields: tachyons, hypothetical faster-than-light particles, the quantum theory of optical coherence, open quantum systems, symmetry and group theory in particle physics, and of course, the Quantum Zeno Effect. Steven Weinberg, who shared the UT Austin Physics Department with Sudarshan for decades, acknowledged in 2006 that it took tremendous courage for Marshak and Sudarshan to propose the V-A structure and praised their courage, physical insight, and elan. George Sudarshan died on May 13, 2018, in Austin, Texas. He was 86 years old. The man who showed the world that watching can freeze reality left behind a body of work that should have earned him the highest honors in physics. The world is worse for not having given them to him, but the prediction he and Misra made needed experimental proof. And that proof was about to come from a laboratory in the Rocky Mountain foothills. David Wineland was born on February 24, 1944, in Wauwatosa, Wisconsin, a suburb of Milwaukee. He earned his doctorate from Harvard in 1970 under Norman Ramsey, who would win the Nobel Prize in 1989. Then he did postdoctoral work at the University of Washington with Hans Demmelt, who shared that same 1989 Nobel with Ramsey. So Wineland learned his craft from two future Nobel laureates, and he would become one himself. In 1975, Wineland joined the National Bureau of Standards in Boulder, Colorado, which later became the National Institute of Standards and Technology, or NIST. He was 31 years old, and he would spend the next 42 years there, building what became arguably the most important ion-trapping laboratory in the world. The problem Wineland was attacking was one of precision. If you want to build an incredibly accurate atomic clock, or if you want to study quantum mechanics at the level of individual atoms, you need to isolate those atoms from everything: heat, stray electric fields, magnetic fluctuations, collisions with other atoms. All of these disturb quantum states and destroy the delicate quantum behavior you want to study. Wineland's approach was to trap ions, electrically charged atoms, using combinations of electric and magnetic fields. Then he would cool them with lasers, slowing their motion until they were nearly perfectly still, nearly perfectly isolated, nearly perfect quantum systems you could study one at a time. In 1978, Wineland demonstrated the first laser cooling of trapped ions using magnesium. In 1981, he isolated a single magnesium ion. By the late 1980s, his group had the tools to do something remarkable. They could prepare thousands of ions in a specific quantum state, manipulate those states with radio frequency pulses and laser light, and measure the results with extraordinary precision. And in 1990, Wayne Itano, Daniel Heinzen, John Bollinger, and Wineland published a paper in Physical Review titled simply Quantum Zeno Effect. It was the experiment the theory had been waiting 13 years for. Here is how it worked. The team loaded about 5,000 beryllium-9 ions into a cylindrical penning trap, which uses a combination of static electric fields and a strong magnetic field to confine charged particles. The ions were laser-cooled to below 250 millikelvin, a quarter of a degree above absolute zero. To appreciate how cold that is, consider this. The surface of Pluto, the coldest major object in our solar system, sits at about 44 Kelvin. Liquid nitrogen, the stuff they use in science demonstrations to freeze roses and shatter them, is 77 Kelvin. Liquid helium boils at 4.2 Kelvin. The cosmic microwave background, the faint afterglow of the Big Bang that pervades all of space, corresponds to a temperature of 2.7 Kelvin. The coldest natural place ever found in the universe is the Boomerang Nebula, about 5,000 light-years away, at roughly 1 Kelvin. These beryllium ions, in a basement in Boulder, Colorado, were at 1/4,000 of a Kelvin. They were about 4,000 times colder than the Boomerang Nebula, about 11,000 times colder than liquid helium, about 300,000 times colder than Pluto. They were among the coldest things in the observable universe, and they were being held there deliberately so that their quantum behavior could be studied without thermal noise destroying everything interesting. For comparison, the coldest natural temperature ever recorded on Earth's surface is about 184 Kelvin, which is about 89 degrees below 0 Celsius. These ions were roughly 700 times colder than that. They were barely moving at all. Beryllium-9 has two hyperfine ground states, which we can call State 1 and State 2. Think of them as two quantum energy levels the atom can sit in, like the ground floor and the second floor of a building. The team prepared all 5,000 ions in State 1. Then they applied a resonant radio frequency field that would, over the course of 256 milliseconds, drive a complete transition from State 1 to State 2 without any interference. After 256 milliseconds, all the atoms would end up in State 2. A complete transition. Every atom moves from the ground floor to the second floor. But then the team introduced the measurements. Short pulses of ultraviolet laser light, each lasting 2.4 milliseconds. When this UV light hits an ion in State 1, the ion fluoresces. It scatters photons that can be detected. If the ion is in State 2, nothing happens. So the UV pulse effectively asks each ion, "Are you still in State 1?" And the act of asking, the act of measuring, collapses the ion's wave function. The team varied the number of UV pulses applied during the 256 millisecond transition period. With 0 measurements, the ions underwent a full transition. 100% ended up in State 2. With 1 measurement in the middle, about half transitioned. With 4 measurements, about 35% transitioned. With 8, about 19%. And with 64 measurements, spread evenly throughout the transition period, the probability of transitioning dropped to less than 1%. Out of 5,000 ions that should have completely changed states, fewer than 50 actually did. The rest were frozen, held in place by the act of observation. Think about what that means concretely. The radio frequency field was still on. It was still trying to push the ions from state 1 to state 2. The force driving the transition had not changed at all. The only thing that changed was that someone was looking, and that was enough to paralyze 5,000 atoms. The results matched the theoretical predictions almost perfectly. The survival probability followed the expected cosine squared function raised to the nth power, where n is the number of measurements. The Quantum Zeno Effect was real. 13 years after Misra and Sudarshan's prediction, and 37 years after Turing first noticed the peculiarity, the theory was confirmed by experiment. When the Nobel Committee called Wineland in 2012 to tell him he had won the Physics Prize, he was sleeping. His wife took the call and woke him up. At a press conference later, with characteristic modesty, Wineland noted that someone had pointed him to a website where the Nobel Prize announcement was on the same page as news about Lady Gaga. So, he said, I guess I have really arrived. He was NIST Boulder's 4th Nobel laureate in 15 years. Before him, Bill Phillips won in 1997, Eric Cornell in 2001, and Jan Hall in 2005. There is something in the mountain air in Boulder, apparently. But there was a legitimate criticism of the Etano experiment that needed addressing. The beryllium ions in a penning trap are not really an unstable system in the way Misra and Sudarshan originally envisioned. The ions are oscillating between two states, driven by an external radio frequency field. It is more like a pendulum being pushed back and forth than like a radioactive atom spontaneously decaying. The Zeno effect was clearly demonstrated for driven oscillations, but did it work for genuine quantum decay? For a system that was truly unstable and falling apart on its own? This distinction matters more than it might seem. Driven oscillations are deterministic, meaning the system follows a predictable path determined by the external field. Spontaneous decay is stochastic, meaning the system has a probability of decaying at any moment, but the exact timing is fundamentally random. These are physically different situations. Showing that you can freeze a pendulum by watching it does not automatically mean you can freeze radioactive decay by watching it. The mathematics predicted both, but mathematics predicts many things that turn out to have subtle complications when you try to observe them in the real world. Several physicists argued that the Etano experiment did not truly demonstrate the Quantum Zeno Effect as Misra and Sudarshan conceived it, but rather a related phenomenon that might have a simpler explanation. The debate was technical and sometimes heated. What was needed was an experiment using a genuinely unstable system, one that decays spontaneously without any external driving force. That question would be answered 11 years later at the University of Texas at Austin, at George Sudarshan's own institution, and it would vindicate the original prediction completely. In 2001, Mark Fisher, Braulio Gutierrez Medina, and Mark Risen, working in the physics department that Sudarshan had called home for over 30 years, published a paper in Physical Review Letters that changed the game. They observed both the Quantum Zeno Effect and its bizarre opposite, the anti-Zeno effect, in a genuinely unstable quantum system. Their setup was elegant. They trapped ultra-cold sodium atoms in an accelerating optical lattice, which is essentially a pattern of standing light waves that creates a series of tiny potential energy wells, like an egg carton for atoms. By accelerating the lattice, they tilted the egg carton so that atoms could quantum tunnel out of their wells and escape. This tunneling process is a genuinely unstable quantum decay, not a driven oscillation. The atoms are spontaneously leaking through a barrier, which is as close to radioactive decay as you can get in a tabletop experiment. To perform measurements, the team would briefly reduce the acceleration, momentarily preventing tunneling, then check how many atoms remain trapped. They could vary the frequency of these measurements and watch what happened to the tunneling rate. At short measurement intervals, around 1 microsecond between measurements, the tunneling was substantially suppressed. Atoms that should have escaped through the barrier were being frozen in place. This was the Zeno effect in a truly unstable system, confirming what Misra and Sudarshan had predicted for exactly this type of scenario. But here is where things got really interesting. At longer measurement intervals, around 5 microseconds, the tunneling rate actually increased. The atoms were decaying faster than they would have without any measurements at all. Observation was not freezing them. It was accelerating their escape. The team had discovered something that theorists had predicted just a few years earlier, the anti-Zeno effect. And they were the first to see both effects in the same system. The anti-Zeno effect sounds like it contradicts the Zeno effect, but it actually emerges from the same physics. When you measure a quantum system, you collapse its wave function, but you also introduce energy uncertainty. Heisenberg's uncertainty principle says that a measurement taking a short time must have a wide energy spread. This energy broadening means the system now overlaps with a wider range of quantum states in its environment. If those states include good decay channels, states the system can easily transition into, then the measurement effectively opens new escape routes. The system decays faster because you gave it more options by looking at it. Whether you get the Zeno effect or the anti-Zeno effect depends on the details. Measure very rapidly, faster than the Zeno time, and you freeze the system. Measure at intermediate rates, and you might accelerate it. The determining factor is how the energy broadening from measurement overlaps with the environmental spectrum. The theoretical framework had been laid out by Abraham Kaufman and Gershon Kuriski in a landmark 2000 paper in Nature. They showed that the Zeno effect requires measurements faster than a critical rate, and that for many real systems, particularly radiative and radioactive decay, the required rate is so extreme that the anti-Zeno effect is actually more common. In their words, the standard quantum Zeno effect is fundamentally unattainable in radiative or radioactive decay because the required measurement rates would disintegrate the system. The opposite effect, acceleration of decay, is much more ubiquitous. Think about what that means for radioactive waste. Just as a thought experiment, you cannot slow down radioactive decay by watching it. The measurements would need to happen on timescales of attoseconds or femtoseconds, and at those rates, you would be pumping so much energy into the atoms that you would destroy them through an entirely different mechanism. For nuclear physics, The Zeno effect remains purely theoretical. But for quantum information science, where the relevant timescales are microseconds to nanoseconds, the Zeno effect is not just possible, it is useful. Before the anti-Zeno effect was seen experimentally at UT Austin, it had been predicted theoretically by Bronislavas Kalakis and Vygantas Gontis at the Institute of Theoretical Physics and Astronomy in Vilnius, Lithuania, in 1997. Their paper in Physical Review A showed that frequent measurements of chaotic quantum systems could cause delocalization, the opposite of the Zeno freezing. This was before Kaufman and Kurisky developed the complete framework, but the Lithuanians got there first with the core prediction. Abraham Kaufman, then at the Weizmann Institute, called the Fisher Group's 2001 experiment outstanding in the spirit of the original proposal of the Zeno effect. It was, in a real sense, the completion of the experimental program. The Zeno effect worked for driven systems, as Itano showed. It worked for unstable systems, as Fisher showed. And its opposite, the anti-Zeno effect, was real too. But the experiments kept coming, and they kept getting stranger. In 2015, a group at Cornell University took the Quantum Zeno Effect out of the realm of atomic transitions and into something you could almost picture happening in real space. Yogesh Patil, Srivatsan Chakram, and Mukund Vengalatore worked with approximately 1 billion rubidium atoms, not 5,000 like the NIST experiment. 1 billion. They cooled these atoms to about 1 nanokelvin above absolute zero, that is 0.000000001 degrees above the coldest possible temperature. To put that in perspective, outer space, the void between galaxies, sits at about 2.7 Kelvin due to the cosmic microwave background radiation. The deepest natural cold we know of in the universe is inside the Boomerang Nebula at about 1 Kelvin. These rubidium atoms were roughly 1 billion times colder than empty space. If the temperature of interstellar space were the height of Mount Everest, 29,000 feet, then the temperature of these atoms would be less than the width of a single bacterium. At these temperatures, the atoms form what is called a Bose-Einstein condensate, a state of matter predicted by Albert Einstein and Satyendra Nath Bose in 1924, but not produced in a laboratory until 1995, when Eric Cornell and Carl Wyman at the University of Colorado achieved it with rubidium atoms and won the Nobel Prize for it 6 years later. A Bose-Einstein condensate is a state where a huge collection of atoms all collapse into the same quantum state and behave as a single quantum object. 1 billion atoms acting as one. The individual atomic identities dissolve, and the entire collection becomes a single quantum entity with a single wave function. It is matter behaving like light, particles behaving like waves, on a scale you can practically see with the naked eye. The team suspended this condensate in an optical lattice, a grid of laser light that creates a repeating pattern of potential wells. Think of it as an egg carton made of light, with each dimple holding a small collection of atoms. The atoms in this lattice can quantum tunnel between adjacent wells, hopping from site to site through barriers that would be impassable in classical physics. This tunneling is one of the most fundamental quantum phenomena. The ability of particles to pass through barriers they do not have enough energy to climb over, simply because their wave function extends through the barrier and gives them a non-zero probability of appearing on the other side. Now here is what the Cornell team did. They shone a laser on the atoms. That is it. They illuminated them with a fluorescence imaging laser and watched. When the laser was off or dim, the atoms tunneled freely through the lattice, spreading out over time as quantum mechanics predicts. But when the laser was bright, when the measurement rate was high, the tunneling was dramatically suppressed. The atoms stayed put. Vengalatori called it the first observation of the Quantum Zeno Effect by real space measurement of atomic motion. Previous experiments had measured transitions between internal quantum states. This one measured whether atoms physically moved from one place to another, and watching them prevented them from moving. An atom sitting in one well of the lattice, which should tunnel to the next well, stayed frozen because someone was watching. The team noted an amusing parallel to the weeping angels from Doctor Who. They're alien creatures that look like stone statues and can only move when nobody is observing them. Except in the quantum world, it is inverted. The atoms are the ones who cannot move when someone watches. Quantum mechanics gives you the opposite of a weeping angel. Call it a Zeno angel. It can only move when you look away. The Cornell experiment also demonstrated the continuous crossover between the weak measurement regime, where atoms tunnel almost normally, and the strong measurement regime, where tunneling is almost completely suppressed. It was not a sharp on-off switch. As you increase the measurement strength, the freezing gradually increases. More watching means more freezing, smoothly and continuously. Since then, the experimental evidence has continued to accumulate across wildly different physical systems. In 2016 and 17, teams working with superconducting circuits, the same technology used in quantum computers, observed Zeno and anti-Zeno effects in single qubits. A 2016 experiment used nitrogen vacancy centers in diamond, tiny defects in a carbon crystal that behave as quantum systems, to create what are called quantum Zeno subspaces, protected regions of quantum state space where information can be stored safely. And in 2024, a group at Lund University in Sweden studied two quantum dots with a single electron bouncing between them and confirmed that increasing measurement strength prohibits the electron from tunneling between dots. Every time someone tests the Quantum Zeno effect in a new system, it works. Trapped ions, ultra-cold atoms, superconducting circuits, diamond defects, quantum dots. The physics does not care about the specific platform. It is a fundamental feature of quantum measurement itself, as physicist Daniel Burgarth put it. It is fair to say that almost anything causes a Zeno effect. It is a very universal and easy to trigger phenomenon, which raises a question that has haunted physicists for 100 years. What exactly is a measurement? This is the measurement problem, and the Quantum Zeno effect turns it from an abstract philosophical puzzle into something visceral and experimental. Because if watching something can freeze it, then the definition of watching matters enormously. What counts as an observation? Does a camera count? Does a photon bouncing off an atom count? Does a human being need to be involved? Does consciousness play a role? Physicist Giovanni Barantini called the Quantum Zeno Effect the apotheosis of the measurement effect, the most extreme demonstration that measurement in quantum mechanics is not a passive process of gathering information, but an active physical intervention that changes the system being measured. In the classical world, Observation is like reading a book. The words do not change because you looked at them. In the quantum world, observation is more like touching a soap bubble. The act of contact changes the thing you are trying to examine. Let us start with what we know for certain. A measurement, in the context that produces the Zeno effect, does not require consciousness. It does not require a human observer. It does not require anyone to look at the results. In 2014, a team led by Augusto Smerzi demonstrated that simply shining a resonant laser on a quantum system with nobody recording or even looking at the output produced the same Zeno dynamics as elaborate projective measurements. The laser light interacted with the atoms, disturbed their quantum states, and that was enough. No mind required. In fact, the research has become even more definitive on this point. Kater Murch's group at Washington University showed in 2017 that even quasi-measurements, interactions that disturb the system but gather no information whatsoever, still produce the Zeno effect. You do not even need to extract data from the system. You just need to disturb it in the right way. The key is not observation in the human sense. The key is interaction, the physical coupling between the quantum system and something in its environment. This matters because it puts to rest a popular misconception that has plagued quantum mechanics since the 1920s. The idea that consciousness causes wave function collapse. The idea that the universe needs a mind to observe it before anything becomes real. This interpretation was championed by Eugene Wigner, a brilliant Nobel laureate who contributed enormously to physics, but whose philosophical leanings on this point have not held up well. Wigner proposed a famous thought experiment in 1961 called Wigner's friend. Imagine Wigner's friend is inside a closed laboratory measuring a quantum system. From the friend's perspective, the measurement has a definite outcome. The atom is spin up or it is spin down. Done. But from Wigner's perspective, outside the laboratory, the entire lab, friend included, is in a superposition of both outcomes. The measurement is not complete until Wigner himself observes the result. If you take the consciousness view seriously, this means the friend inside the lab does not have a definite experience until Wigner looks, which is, to put it mildly, weird. In 2019, an experimental test at Heriot-Watt University in Edinburgh confirmed that Wigner's scenario leads to genuinely irreconcilable perspectives. Different observers can disagree about objective facts, but the resolution does not require consciousness. It requires understanding that measurement is a physical process, not a mental one. In 2022, philosophers David Chalmers at NYU, one of the most prominent philosophers of mind in the world, and Kelvin McQueen at Chapman University published a paper titled Zeno Goes to Copenhagen that addressed this directly. They analyzed whether the Quantum Zeno Effect supports the consciousness causes collapse interpretation and concluded that saving this view requires what they called a very strong form of mind-body dualism, one where consciousness does not depend on brain states at all. This is a view that essentially nobody in physics or neuroscience holds. The argument is particularly devastating when you consider quantum biology. The Quantum Zeno Effect appears to play a role in how certain proteins function inside living cells, how birds navigate using Earth's magnetic field, how photosynthesis captures light energy with extraordinary efficiency. These are processes that occur in plants, bacteria, and bird retinas. If the Zeno effect required consciousness to trigger measurements, then you would need to accept that plants are conscious, that bacteria are conscious, that the proteins inside a migrating bird's eye are having subjective experiences. The alternative, which essentially all physicists accept, is that measurement is a physical interaction, not a mental event. This connects to the deepest divide in the interpretation of quantum mechanics. The Copenhagen interpretation says measurement causes collapse, but defines measurement as any interaction with a classical apparatus, no consciousness needed. The many worlds interpretation says there is no collapse at all. Every possible outcome happens in a different branch of reality. And what we experience as the Zeno effect is simply the fact that in the branches we inhabit, the system keeps being found in its initial state. The decoherence interpretation says that interaction with the environment effectively selects certain quantum states as stable, and measurement is just a particular kind of environmental interaction that pins the system to a specific state. All of these interpretations predict the same experimental results for the Zeno effect. They differ in what they say is really happening behind the math. And the Zeno effect, precisely because it makes the role of measurement so dramatic and so undeniable, forces physicists to confront these interpretational questions, whether they want to or not. There is one more philosophical angle worth exploring before we move on. The folk saying that a watched pot never boils is, in everyday life, simply false. The pot boils at the same rate whether you stare at it or go do something else. Time just feels slower when you are waiting. The saying is about psychology, not physics. In the quantum world, the saying becomes literally true. A watched quantum pot genuinely never boils. When the Cornell team published their 2015 results, the university's press release led with exactly this angle. In the quantum world, the folk wisdom really is true. There is something almost poetic about this. A piece of folk wisdom that was always wrong in the classical world turns out to be exactly right in the quantum world, as if the intuition was 2,000 years ahead of the physics that would justify it, pointed at the wrong level of reality, but capturing something true about a deeper one. So the quantum Zeno effect is real. It is experimentally confirmed. It is philosophically profound. But is it useful? Can you actually do anything with the ability to freeze quantum systems by watching them? The answer, it turns out, is yes, and the applications range from the cutting edge of quantum computing to something so ordinary you might have seen it this morning outside your window: birds. Let us start with quantum computers, because that is where the Zeno effect is having its most immediate technological impact. The fundamental problem with quantum computing is decoherence. A quantum computer stores information in qubits, quantum bits that can exist in superpositions of 0 and 1 simultaneously. This is what gives quantum computers their power. A classical computer with 3 bits can represent one of 8 possible states at a time. A quantum computer with 3 qubits can represent all 8 states simultaneously, and performing operations on the superposition effectively processes all 8 in parallel. Scale this up to a few hundred qubits, and you have a machine that can, in principle, solve certain problems that would take a classical computer longer than the age of the universe. But superpositions are fragile, incredibly fragile. any interaction with the environment, a stray photon, a magnetic field fluctuation, a vibration in the table, even the thermal radiation from the walls of the room can cause the qubits to decohere, meaning their quantum superposition collapses into a definite classical state. When that happens, the quantum advantage evaporates. The computation fails. To appreciate how fragile, consider the timescales. The best superconducting qubits today maintain their quantum states for about 100 to 300 microseconds before decoherence destroys them. That sounds incredibly short, and it is. But a quantum logic gate, a single step in a quantum computation, takes roughly 20 to 50 nanoseconds. So you get maybe a few thousand gates before the qubit falls apart. For comparison, a classical computer performs billions of operations per second, and its bits never randomly flip. Imagine if your laptop could only perform a few thousand calculations before the numbers in memory randomly changed. That is the situation quantum computers face. The problem gets worse as you scale up. More qubits means more opportunities for environmental noise to creep in. More connections between qubits means more pathways for decoherence. And the errors compound. If each qubit has a 1% chance of error per gate, then after 100 gates on 100 qubits, you are almost guaranteed to have several errors. And in quantum computing, errors do not just give you wrong answers. They can corrupt the quantum state of the entire system, spreading from one qubit to many through entanglement. This is not a minor engineering problem. It is the central challenge of quantum computing, and many researchers believe it is the single biggest obstacle between where we are now and a quantum computer that can solve problems. No classical computer ever could. Current quantum computers operate at temperatures colder than outer space, are shielded from electromagnetic interference, are isolated from vibration, and still their qubits decohere in microseconds to milliseconds. Building a useful quantum computer requires either making qubits that last much longer, or developing error correction schemes that can fix decoherence faster than it occurs. And this is where the Quantum Zeno Effect enters the picture. If you can freeze a quantum state by watching it, then maybe you can protect quantum information from decoherence by strategically watching your qubits. The formal connection was established in a 2004 paper by Paolo Facci, Daniel Lidar, and Saverio Pascazio. They showed that the Quantum Zeno Effect and a technique called bang-bang dynamical decoupling, which was already being used in quantum computing, are actually the same physical mechanism seen from different angles. Both techniques work by creating what are called quantum Zeno subspaces, regions of the quantum state space that are effectively walled off from each other by frequent measurements or strong interactions. Within a Zeno subspace, the qubit can evolve and perform computations freely, but transitions out of the subspace, which would represent errors or decoherence, are suppressed by the Zeno effect. Think of it like putting a marble in a bowl. The marble can roll around freely within the bowl, which represents useful computation, but it cannot escape over the rim, which represents errors. The Zeno effect creates the bowl. Without it, the marble is on a flat table and can roll anywhere, including off the edge. 3 equivalent methods can create this protection. First, pulse projective measurements, essentially measuring the qubits frequently to check if they have left the desired subspace. Second, continuous strong coupling, attaching the qubits to an external system that continuously interacts with them in a way that suppresses unwanted transitions. Third, pulsed unitary kicks, the bang-bang method, where rapid control pulses effectively scramble the decoherence before it can accumulate. All three are manifestations of the same underlying physics. The Quantum Zeno Effect is not just a curiosity, it is the theoretical foundation for an entire class of quantum error correction methods. In 2012, Paz Silva, Rebentrost, Aspuru Guzik, and Lidar published a paper in Physical Review Letters demonstrating that the Zeno effect can protect appropriately encoded arbitrary quantum states to arbitrary accuracy while still allowing universal quantum computation. This was a major result because it showed you do not have to choose between protection and computation. You can have both. The Zeno subspaces are large enough to compute in, but walled off from the error causing outside. More recently, in 2023, researchers developed what they call Zeno gates, multi-qubit entangling operations that exploit the Zeno effect to create quantum logic gates between qubits that do not even directly interact with each other. The measurements themselves mediate the interaction. The act of watching creates the gate. This approach is particularly promising for circuit quantum electrodynamics and cavity quantum electrodynamic systems, two of the leading platforms for building quantum computers. The same year, a team developed high-fidelity Zeno gates specifically designed for cat qubits, a type of quantum bit that uses superpositions of large coherent states to encode information with built-in protection against certain types of errors. Their four innovative gate designs achieved exponential scaling of gate errors, meaning the errors shrink exponentially as you increase the control parameter. For a field where reducing error rates by even a factor of 2 is newsworthy, exponential improvement is remarkable. And at Fermilab, the Superconducting Quantum Materials and Systems Center, which is funded by the Department of Energy, has proposed using the Quantum Zeno Effect to decouple a specific type of defect called a two-level system from superconducting qubits. These defects are one of the main factors limiting qubit lifetimes in current quantum computers. If the Zeno approach works, it could extend qubit coherence time significantly, which is one of the most important practical challenges in the entire field. So the effect that started as a thought experiment by an ancient Greek philosopher was rediscovered by a tragic genius in Texas and was confirmed by a future Nobel laureate in Colorado, is now being engineered into the machines that many people believe will define the next era of computation. The watched pot that never boils is becoming a tool for protecting the most delicate information in the universe. But the application that I find most astonishing is not in a quantum computer. It is in a bird's eye. Every autumn, billions of migratory birds navigate thousands of miles with extraordinary precision. Arctic terns fly from the Arctic to the Antarctic and back, a round trip of roughly 44,000 miles, which over a 30-year lifespan adds up to more than 1.5 million miles of migration. That is about 3 round trips to the moon. Bar-tailed godwits fly from Alaska to New Zealand non-stop, over 7,000 miles without resting, eating, or drinking, in a single flight that lasts 8 to 10 days. European robins migrate from Scandinavia to the Mediterranean and back. Monarch butterflies, though not birds, travel from Canada to a specific patch of forest in central Mexico, arriving at the same trees their great-great-grandparents left from, despite no individual butterfly ever having made the trip before. And these navigators achieve a precision of roughly 5 degrees, which is better than most humans can manage with a compass and a map. How? Part of the answer involves landmarks and the sun and the stars, but a crucial component, especially for navigation on overcast days and during nighttime migration, is that birds can sense Earth's magnetic field. They have an internal compass. This has been demonstrated repeatedly since the 1960s through elegant experiments where birds in planetariums with manipulated magnetic fields change their preferred migration direction accordingly. But the mechanism was deeply puzzling. The magnetic field of the Earth is absurdly weak by the standards of physics. At Earth's surface, it ranges from about 25 microtesla near the equator to about 65 microtesla near the poles. For context, a typical refrigerator magnet produces a field of about 5,000 microtesla, roughly 100 times stronger. An MRI machine operates at 1.5 to 3 Tesla, about 50,000 times stronger than Earth's field. The magnetic field that these birds detect is a whisper in a world of shouting. How can a biological system built from wet, warm, sloppy protein chemistry at body temperature detect something that faint? The leading theory involves a protein called Cryptochrome, found in the retinas of migratory birds. Cryptochrome is a blue light photoreceptor, meaning it absorbs blue photons from sunlight. When light hits cryptochrome, it triggers a chain of electron transfers within the protein that creates what is called a radical pair, 2 molecules each with an unpaired electron. Normally, electrons come in pairs with opposite spins, cancelling each other out magnetically. But these radical pairs have lone electrons whose spins are exposed to the environment. These unpaired electrons have quantum spin, and the spins of the 2 electrons become entangled, correlated in a way that has no classical explanation. The 2 electrons, even though they are on separate molecules within the protein, share a quantum state. The relative orientation of these entangled spins is sensitive to external magnetic fields, even very weak ones like Earth's field. A tiny change in the external field alters the quantum dance between the 2 spins, which changes the probability of the radical pair recombining or separating. These different chemical fates, recombination versus separation, produce different downstream signals in the protein. The bird's nervous system detects these differences and translates them into navigational information. The bird literally sees the magnetic field, perceiving it as a pattern overlaid on its visual field, like a heads-up display made of quantum physics. This is already remarkable, a biological system exploiting quantum entanglement for navigation. But there was a problem. The sensitivity of the radical pair mechanism, as originally proposed, was not good enough to explain the precision birds actually achieve. The magnetic field differences that birds can detect are so tiny that the standard radical pair model could not account for them. Enter the Quantum Zeno Effect. In 2008, Ioannis Komenis at the University of Crete proposed that the Quantum Zeno Effect underlies the radical pair magnetoreception mechanism. The idea is that certain molecular processes within the cryptochrome protein effectively act as repeated measurements on the radical pair's spin state. And these measurements create Zeno-type dynamics that dramatically enhance the system's sensitivity to weak magnetic fields. In December 2024, the Katnick Group at the University of Exeter published a groundbreaking paper in Nature Communications, providing detailed evidence for this mechanism. They showed that tightly bound radical pairs in cryptochrome, specifically involving a molecule called FAD and superoxide, can respond to Earth-strength magnetic fields through asymmetric recombination dynamics that invoke the Quantum Zeno Effect. This was a result that had previously been thought impossible for such small magnetic fields. Then in September 2025, a paper in AVS Quantum Science by Smith and colleagues demonstrated that a phenomenon called chirality-induced spin selectivity, which is related to the handedness of biological molecules, reinforces the Quantum Zeno Effect in cryptochrome. The combination creates magnetic sensitivity with approximately 5-degree precision, which is exactly the kind of accuracy that birds actually demonstrate during migration. Stop and think about that for a moment. The same quantum effect that was proposed by a philosopher in ancient Greece, formalized by 2 physicists in Texas, and demonstrated with trapped ions in Colorado, is operating inside the eyes of birds. Evolution discovered the Quantum Zeno Effect billions of years before humans did, and has been using it to navigate migratory birds across the planet. A robin flying from Norway to Spain is exploiting the same physics that engineers are trying to build into quantum computers. Nature, as usual, got there first. The Quantum Zeno Effect has also found its way into commercial technology, specifically in the field of atomic magnetometry. Magnetometers that measure extremely weak magnetic fields have enormous practical applications, from detecting unexploded ordnance to imaging brain activity to mineral exploration. The most sensitive atomic magnetometers work by observing the behavior of alkali metal atoms, typically rubidium or potassium, in dense vapor form. In these systems, there is a process called spin exchange relaxation that normally destroys the quantum coherence needed for sensitive measurements. But it turns out that in dense enough vapors, the spin exchange collisions happen so frequently that they effectively perform continuous measurements on the atomic spin states, invoking the Quantum Zeno Effect and actually suppressing the relaxation rather than causing it. This is the basis of surf magnetometers, spin exchange relaxation-free magnetometers, and they are the most sensitive magnetic field detectors ever built. Companies are already commercializing this technology. Circa Magnetics in Nottingham, England, is developing room temperature brain imaging sensors that can detect the tiny magnetic fields produced by neural activity. Q.ANT in Germany makes a commercial quantum magnetometer called the Q.M10 that can measure biosignals in the picotesla range, which is about a billionth of the strength of a refrigerator magnet. And QC Tehrel in Australia is developing rubidium-based quantum magnetometers for NASA's Artemis program to do geological surveys on the moon. The watched pot that never boils is, in the most literal possible sense, being sent to the moon. There is something even more remarkable about quantum Zeno subspaces that goes beyond simply protecting quantum information. It turns out that the Zeno effect does not just freeze quantum systems. It can sculpt them. It can force quantum evolution to follow paths it would never take on its own. And this was demonstrated beautifully by a Nobel laureate using some of the most exotic atoms in physics. In 2014, Serge Haroche and his team at the École Normale Supérieure in Paris, working with Rydberg atoms, showed that the Quantum Zeno Effect could be used to create Schrödinger cat states, superpositions so large and so delicate that they normally cannot exist for more than a tiny fraction of a second. Rydberg atoms are atoms where an electron has been kicked up to an absurdly high energy level. The electron orbits so far from the nucleus that the atom swells to enormous size by atomic standards. A Rydberg atom with a principal quantum number of 50, which is what Haroche's team used, has an electron orbit roughly 130,000 times larger than a ground-state hydrogen atom. If a normal hydrogen atom were the size of a golf ball, a Rydberg atom at quantum number 50 would be the size of a building. These bloated atoms have extraordinary properties. They are incredibly sensitive to electric and magnetic fields. They interact with microwave radiation, and because they have so many energy levels packed closely together, 51 distinct states in Haroche's experiment, they can undergo all kinds of complex quantum transitions. Haroche's team used microwave fields to divide the 51 Rydberg states into two groups, say states 1 through 25 and states 26 through 51. They applied radio frequency pulses that would normally cause atoms to hop freely between all 51 states, including jumping between the two groups. But by performing frequent measurements that checked which group the atom was in, they invoked the Quantum Zeno Effect and blocked transitions between groups while allowing free evolution within each group. The result was that the atom could explore all the states within its group, but was forbidden from crossing to the other group. The Zeno measurements created a wall in the middle of the quantum state space, and by carefully preparing the initial state, the team could create superpositions of states that were trapped on one side of this wall, producing Schrödinger cat states, quantum superpositions of macroscopically distinct configurations that were protected by the Zeno dynamics. This is the Zeno effect, not as a brake, but as a steering wheel. You are not just preventing change, you are channeling it, allowing evolution in certain directions while blocking it in others. The measurements create a landscape of permitted and forbidden transitions, and the quantum system navigates that landscape according to rules you set by choosing what to measure and how often. Serge Haroche shared the 2012 Nobel Prize with David Wineland, the same David Wineland whose team did the original 1990 Zeno experiment. Both were honored for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. It is fitting that both Nobel laureates in that year had deep connections to the Quantum Zeno Effect. There is one more area where the Quantum Zeno Effect connects to frontier physics, and it involves something called time crystals. A time crystal is a phase of matter that breaks time translation symmetry, which means it repeats periodically in time the way a regular crystal repeats periodically in space. A normal crystal has atoms arranged in a pattern that repeats every certain number of nanometers. A time crystal has a quantum state that returns to itself after a certain time period, spontaneously oscillating without absorbing or releasing energy. The concept was proposed by Frank Wilczek, a Nobel laureate, in 2012, and the first experimental demonstrations appeared in 2017. The connection to the Quantum Zeno Effect is that Zeno subspaces, those protected regions of quantum state space created by frequent measurements, can support time crystal behavior. Competition between strong measurements and the system's natural dynamics can induce the spontaneous time translation symmetry breaking that defines a time crystal. Measurements create the protected space. The dynamics create the oscillation within that space. Together, they produce a time crystal. In 2024, a team at the University of Chinese Academy of Sciences used a discrete time crystal to protect a fragile 36-qubit entangled state known as a GHZ state. A Greenberger-Horn-Zeilinger state is one of the most delicate forms of quantum entanglement. Lose a single qubit, and the whole thing collapses. The time crystal acted as what the researchers called a safe house for the entangled state, protecting it from decoherence. This was described as the first practical application of a discrete time crystal, and it works, at least in part, because the Zeno effect creates the protected subspace that the time crystal inhabits. So now we have the Quantum Zeno Effect connecting to ancient philosophy, to quantum computing error correction, to bird navigation, to commercial magnetometry, to lunar exploration, and to exotic new phases of matter. For a concept that started as a peculiar thought experiment about arrows, that is an extraordinary reach. Let me take you back to something I mentioned earlier, because it deserves more attention: the relationship between the Quantum Zeno Effect and Schrödinger's famous cat. You know the setup. A cat is sealed in a box with a vial of poison connected to a quantum trigger. If a radioactive atom decays, the trigger breaks the vial and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics says that before anyone opens the box, the atom is in a superposition of decayed and not decayed, which means the cat is in a superposition of alive and dead. The act of opening the box and looking, of measuring, collapses the superposition into one outcome or the other. Now imagine, instead of waiting an hour and then checking the box once, you peek into the box 1,000 times a second. Each peek is a measurement. Each measurement collapses the system. If the atom has not decayed yet, which is extremely likely in the first microsecond, the measurement collapses it back to the undecayed state. The clock resets. You peek again. Same thing. The atom keeps getting caught before it can decay. 1,000 peaks per second might not be enough, depending on the atom's half-life. But in principle, if you could peak fast enough, continuous observation would prevent the atom from ever decaying. The poison is never released. The cat lives forever. The Quantum Zeno Effect lets you save Schrödinger's cat by refusing to stop watching it. Conversely, the anti-Zeno effect means that peaking at the wrong rate could accelerate the atom's decay and kill the cat faster. The timing of your observations determines whether the cat is saved or doomed, which is a disturbing amount of power for a peak to have. This is ultimately what makes the Quantum Zeno Effect so philosophically provocative. It is not just that measurement affects quantum systems. We have known that since the 1920s. It is that measurement can completely override the natural dynamics of the system. The atom wants to decay. The laws of physics say it should decay. The energy is available. The decay channel is open. Everything is in place for the transition to happen. And yet, a sufficiently attentive observer can prevent it, not by doing anything to the atom, not by applying a force or changing the conditions, just by looking. In classical physics, the universe does its thing, and you watch. In quantum physics, the universe does its thing unless you watch, in which case, it does whatever the watching allows. There is a beautiful visual demonstration of Zeno-like physics that does not require a laboratory at all. You can do it with 3 polarizing filters, the kind you find in sunglasses or photography equipment. Take 2 polarizing filters and orient them at 90 degrees to each other, 1 vertical and 1 horizontal. Light passing through the first filter becomes vertically polarized. The second filter, being horizontal, blocks all vertically polarized light. No light gets through. 0. This is just classical optics. Nothing quantum about it. Now insert a third polarizing filter between the first 2, oriented at 45 degrees. You would think that adding another barrier would block even more light. Instead, light now passes through all 3 filters. Some light makes it through the first filter as vertically polarized. The 45-degree filter projects this onto its axis, letting some through now polarized at 45 degrees. The horizontal filter then projects this again, letting some through as horizontally polarized. Light that was completely blocked by 2 filters can now pass through 3. Add more intermediate filters at smaller angular increments, and even more light gets through. In the limit of many filters with tiny angular differences between them, nearly all the light passes. Each filter is effectively a measurement that rotates the polarization by a small amount. The many small measurements guide the light smoothly from vertical to horizontal polarization, something that was impossible with just 2 filters. This is the inverse of the Zeno effect, more like the anti-Zeno effect, but it illustrates the same core principle. Measurement changes quantum states, and the timing and frequency of measurements determines the outcome. With no intermediate measurements, the polarization cannot rotate from vertical to horizontal. With many intermediate measurements, it rotates smoothly. The measurements are not passive observations. They are active interventions that shape what happens. We are nearing the end of this story, and I want to come back to where we started, to that laboratory in Boulder, Colorado, to 5,000 beryllium ions hovering in a magnetic trap, colder than almost anything in the natural universe. What Wayne Itano and David Wineland demonstrated in 1990 was not just a confirmation of a theoretical prediction. It was a demonstration of something deeply unsettling about the nature of reality. The quantum world, the layer of reality that underlies everything you see and touch and experience, is not indifferent to observation. It is exquisitely sensitive to it. The act of looking changes what is there to be looked at. The act of measuring determines what is measured. This is not mysticism. This is not a metaphor for mindfulness or consciousness or any of the pseudo-spiritual interpretations that sometimes get attached to quantum mechanics. This is a measured, reproducible, physical phenomenon that has been confirmed in dozens of laboratories using every major quantum technology platform available. It is as real as gravity, and it connects across 2.5 millennia to a philosopher who bit off a tyrant's ear. Zeno of Elea was not trying to do physics. He was trying to do philosophy, to show that our intuitive beliefs about motion and change contain hidden contradictions. He succeeded. His paradoxes troubled the greatest minds in mathematics for over 2,000 years. They helped drive the development of calculus, of set theory, of our modern understanding of infinity and continuity, and they gave their name to a quantum effect that Zeno himself could never have imagined. Here is the deepest irony. Zeno argued that the flying arrow cannot move because at each instant it is at rest, and an infinite concatenation of rests cannot produce motion. He was wrong about classical arrows. Classical mechanics, once properly formulated with calculus, shows perfectly well how instantaneous states of rest combine to produce continuous motion. The paradox is resolved. But Zeno was right about quantum arrows. A quantum system that is measured at each instant really does remain at rest. An infinite concatenation of quantum measurements really does prevent quantum motion. The paradox is not resolved, it is confirmed. 2,500 years later, the physics caught up with the philosophy, and the philosophy won. George Sudarshan, the man who named this effect and connected it to Zeno's ancient insight, spent his career being overlooked by the institutions that should have celebrated him. He was passed over for the Nobel Prize at least 9 times, watched others receive credit for his discoveries, and ultimately made peace with it by doing science for its own sake. He and Baidyanath Misra wrote their paper in 1977, and it launched an entire field. Alan Turing noticed the same peculiarity in 1953 and was told it was not important. He died the following year without publishing the insight. 23 years later, Misra and Sudarshan proved he was right. David Wineland spent decades developing the tools needed to test the prediction. And in 1990, his team showed it was real. 22 years after that, the Nobel Prize Committee called while he was sleeping. Mark Fisher, working in the same department where Sudarshan spent his entire American career, demonstrated the effect in a truly unstable system in 2001 and saw the anti-Zeno effect for the first time. The Cornell team in 2015 showed that you could freeze 1 billion atoms in place just by shining a light on them. And right now, engineers at companies and national laboratories around the world are building the Quantum Zeno Effect into quantum computers, magnetometers, and sensing technologies. The philosophical curiosity became an experimental fact, became an engineering tool. Meanwhile, somewhere over the Atlantic Ocean, a European robin is flying south for the winter, navigating with a precision of 5 degrees, using a quantum compass in its retina that exploits the very same effect. Evolution built the tool 300 million years ago when the first magnetoreceptive organisms appeared. Physics named it in 1977. Technology started using it in the 21st century. The universe, it turns out, has always cared whether you are watching. We just took a while to notice. There is a line from Sudarshan that I keep coming back to. He wrote that the universality of science does not imply unbiased acclaim for scientific truth. He meant it as a lament about his own career, about the Nobel Prizes that should have been his, about the credit that was given to others. But I think it applies more broadly. The Quantum Zeno Effect tells us something universal about how the quantum world works. Observation is not neutral. Measurement is not passive. The act of looking is an act of intervention. This is true whether a Nobel committee acknowledges it or not. It is true whether the observer is a laser in a laboratory, a protein in a bird's eye, or a philosopher in ancient Greece staring at an arrow in flight. The arrow does not fly because you are watching it. 2,500 years ago, Zeno said that, and everyone thought he was playing games with logic. Now we know he was describing reality, just not the one he could see. The watched quantum pot never boils. The frozen atom never decays. The observed particle never tunnels. And the arrow, Zeno's arrow, the one that was supposed to be a paradox, turns out to be the most literal description of quantum mechanics anyone has ever given. You can freeze reality by watching it. Physics said so. Experiments confirmed it. And a Greek philosopher figured it out 25 centuries early. He just did not know he was talking about quantum mechanics.